Good evening, everyone. So today we look at the solutions from INMO 2020. Okay, so basically, I had some unfinished slides of this of the solutions for a long time, and today I decided to complete it. So all right. So as usual, there were 6 problems and 4 hours. Okay. So this is problem 1. It says there are 2 circles, gamma 1, gamma 2, and centers are O1, O2, like this, and they intersect at points A and B. Okay. And then you assume that the center of each circle is outside the other circle. So this arrangement is okay. And after that, it says the tangent to gamma 1 at B intersects gamma 2 at C, and tangent of gamma 2 at B intersects gamma at D. So you draw tangents to the 2 circles. So one of them is, this point is D, this point is C. So this line is a tangent to this circle. This line is a tangent to this circle. Okay. And after that, what it says, it says the bisector of angle DAB and CAB. So DAB. So this also you join it. So bisector of this and bisector of that intersects again circle at X and Y. So that if you draw the bisector, it will intersect here at X. Bisector of this intersects at Y. Okay, and then it says P and Q be the circumcenter of triangle ACD. So ACD, this one, and XAY, this triangle. You find the circumcenter of that. So instead of drawing a circle, which will complicate the diagram, so basically I take 2 sides and I take the midpoint of that and I draw a perpendicular to that. So, and the intersection point will be the circumcenter. Yes. So if I draw a perpendicular to this, of course it will pass through O1. Perpendicular here will pass through O2. So basically I just join these, extend it, join these 2 points, extend it, and where they intersect, that will be the. So this is the required circumcenter. Okay, and same thing here. You take these 2 lines, find the midpoints, and you join these two, and you extend it. So this will be the circumcenter of AXY. Okay, and then it says prove that PQ is perpendicular bisector of O1, O2. So this PQ, this line PQ, it bisects O1, O2. So to here you kind of see that maybe these 2 red lines, they look equal, and these 2 also, they look equal. Okay, so if you can just show this, these 2 lines are equal, probably then you can show it easily. So this is what we will show. So we will show this line equals this line, and this line equals this line, and after that it's just a 2-line proof to show that this line will bisect this. Okay, so we just start with the first part. So you have this circle, we draw the tangent of this one, tangent to this one, and join these 3 segments, take the midpoint, and you join this and join this, and this is the circumcenter of ACD. Okay, so you have to show that this equals this. So what I basically do is I join these lines also. I join this O1, O2, 1B, and also join these. And now I start. Okay, so you look at this angle here, this one. So it's subtended by the chord AB. So the angle that this chord AB will subtend at the center is double of that. And since this will bisect, so these 2 angle I is equal to this. So this 2 also I can mark with red. And now here we can see that this is this line BC is basically perpendicular to the line O1B. Okay, and this is 90 degrees. So this is pi by 2 minus this angle. So this angle will be equal to the complement of that. So this angle ABC will be equal to this. Okay, because this is 90. So angle O1BA will be equal to 90 minus this. And since O1BC is 90, so this is equal to that. Okay, and now you can continue. This angle is basically subtended by this chord AC, so AC will subtend the double of this at the center, and this is a bisector here, so these two angles will be also equal to this red angle here. Okay, so we have this, and now you look at the other angle, this one. This is subtended by the chord AB, so AB will subtend double of this on the center, and this is a bisector here, so these two angles will be same as this. And with the same logic, this angle here, ABD, will be same as the blue. So this is subtended by this chord AD. So AD will subtend the double of this on the center. Yeah. So and this is the bisector. So these two will be equal to the blue angles. And now you have your results. So you basically look at this triangle PO1O2. So this base angle is red plus blue. This base angle is red plus blue. So these two base angles are equal. That means the lateral sides are equal. So these two red lines, they are equal. So this is part 1. And similarly, we can also prove the part 2 is just one more step. So we have this configuration. We draw the angle bisectors, and you take the midpoint and you join that. So this will be perpendicular here. This will be perpendicular. This will be 90 degrees. And what you had from the previous result was this blue angle was equal to this blue angle. This red angle was equal to this red angle. So that means this angle DAB, triangle DAB, and triangle ABC, they are similar. Okay, because two angles are equal, so third angle is also equal. So this angle DAB will be equal to angle BAC. And this is bisector here, so that means all the four angles here will be equal. So I just call it as four green angles. They are all equal. So that's step 1, and now you have just you are just about to get the result. You look at this triangle here, which I marked in bold. So this is 90 degree here. This is 90 degree here. These two angles are equal. So that means this triangle is similar to this triangle. So that means this third angle will be equal to the green angle here. So this angle will be equal to this angle. And similarly, in the other one, I just extend this and to the intersection point, and I look at this triangle here, this triangle and this smaller triangle here. So again, one angle is common. One angle here is 90, one angle here is 90. So this third angle will be equal to the green angle, and this is equal to the opposite angle here. That will also be equal to the green angle here. So this is also green. That means these two base angles are equal. That means so O1Q will be equal to O2Q. So that's your results. And so this is the configuration that we have. So sorry, this should be O1. So O1Q will be equal to O2Q, and O1P will be equal to O2P. And now you have to show that if you join this and you take the midpoint, so this will be collinear. So if you draw a straight line through P and Q, it will pass through midpoint. So basically, yeah, it's just one line proof. From this you join P, from this you join Q. So in this isosceles triangle, this is the median, but since it's isosceles, so the median will be a perpendicular bisector. So this angle is pi by 2. Similarly, here it's isosceles, so this angle is pi by 2. That means this is a straight line. Okay, so this straight line bisects this straight line. And so that was what you had to prove. So it is yeah, so it was a simple problem, but it can easily get confusing. So this is problem 2. So there is a polynomial and real coefficients. It says P of cos theta plus sin theta is P cos theta minus sin theta for every theta. Then show that you can write Px in this form. Okay, so how do we do this? So first of all, this one I can write it as, you know, as I divide by root 2 and multiply by root 2. This will become cos sin theta plus 5 by 4, and this will become cos theta plus pi by 4. So, and theta plus pi by 4, I can call it phi. So this becomes this. P of root 2 sine phi is equal to P of root 2 cos phi. So yeah, from here, there are many ways to actually prove it, but I'll just show you the most direct one. So basically, you put phi equal to minus pi by 4, you get P of minus 1 here and P of 1 here, so they are equal. So call it A naught. So that means x plus 1 and x minus 1. They will divide Px minus A naught. Okay. So you can write Px as A naught plus x plus 1 into x minus 1 of some another polynomial Qx. So you can write it in this form. A naught plus x squared minus 1 of Qx. So I'm just trying to get it in this form here. So after that, you again put this P of root 2 sine phi equal to P of root 2 cos phi. You apply it here and you put that twice. So this term A naught will go away, and what you will have here is 2 sine square phi minus 1. Here is 2 cos square phi minus 1, and this will be minus cos 2 phi, and this will be plus cos 2 phi. So what you basically get is this term will go out, and you get q of root 2 sine phi is minus q of root 2 cos phi. So here they are equal, but here they are negative of each other. So q is kind of opposite to that. So okay, this is the form we have to get, and now let's continue. So we have this, and after that we have seen that q of root 2 sine phi is minus q of root 2 cos phi. Again, you put some values, put phi equal to pi by 4, you get q of 1 will be minus q of 1. Both will be 1. That means q of 1 is 0. So that means x minus 1 divides qx. Similarly, if you just put pi by 4 plus pi, this will become minus 1, and this also will become minus 1, and you will have a minus sign still here. So that means q of minus 1 is 0. So x plus 1 also divides qx. So qx, again, you can write it as x plus 1 into x minus 1 of p1x. So x squared minus 1 times px. So this you substitute here. So px becomes this. So now I again have this kind of getting to this form here. So this, we have seen this, and now if you look at p1x and you put this p of root 2 sine phi equal to p of root 2 cos phi, you put it here, and what you see is that since there's a square here, so this will become cos 2 phi whole square, and this will be minus cos 2 phi whole square. So this time there's no negative sign, and basically what you get is this p1 of root 2 sine phi equal to p1 of root 2 cos phi. So p1 has same properties of p. Okay, just that it's the power of the polynomial will be smaller. Okay, so p1 has same properties of px, except that the power has decreased. So you can write this as this, and p1 you can again write it in this form. Okay, so you can write it as a1 plus some p2x. So p2x again will have same form, and then you can continue this way. And finally, since it's a polynomial of finite power, the powers of p1, p2 will keep on decreasing. It will finally become 0. And the form, even the way, if you when you extend this, you will end up with this form here. Okay, so that was a straightforward proof of this. Okay, let's look at next problem. This is also, I thought, was quite simple. So take this set x from single digit numbers 0 to 9, and then it says S is a proper, not a proper, S is a subset of x such that any positive integer n can be written as p plus q, where the non-negative integers pq have all their digits in S. So p and q, all the digits are coming from S. Okay, so find the smallest possible number of elements of S. So the smallest cardinality of S, that's possible. You will find that. So yeah, so first of all, 1 can be written as only 0 plus 1. So from there you can see that 0 and 1 has to be in S. Okay. 3 you can write it as 0 plus 3 or 1 plus 2. So either 2 or 3 has to be in S. So S is at least this. It's 0, 1, 2 or 0, 1, 3. I mean minimum. Yeah. So there are probably more elements here. We'll see. And if you look at 5, you can write it as 0 plus 5. So you add 5 here, or you can write it as 1 plus 4. So you can write 1 and 4. Or you can write 2 and 3. So we have this. Here also you can write 0 plus 4. So I mean 0 plus 5 here. So you'll get this 0, 1, 3, 5. Or you can get 1 and 4. 1 and 4. So it will be 0, 1, 3, 4. Or you can get 3 and 2. So that's already there. 3 and 2. So S is, now we see with 5, S is minimum. This is obviously not enough because 9 you cannot write it here. Okay. So there will be more elements in this because 9 is not included. So if you want to write 9, you have to put more numbers here. So the cardinality of S is less than equal is more than equal to 5. Okay. But with 5 it's possible. You take 0, 1, 3, 4, 5 and then every number you can write it. You can write 1 as 0 plus 1, 2 you can write 1 plus 1, 4 is already there, 5 is already there, 6 you can write 3 plus 3, 7 you can write 4 plus 3, 8 you can write 4 plus 4, 9 you can write 4 plus 5. Okay. So any number that you have, you can just write it as from elements of this. So you have 972, 9 you can just split it 5, 4, 7 split it as 4, 3, 2 split it as 1, 1. So any number you can just write it from this set. Okay, so it's equal to 5. That's your answer. I think this was a very simple problem. Okay, so this is problem 4. This is also a nice one. So it's you're given an integer n greater than or equal to 2, and you are given this sequence of non-decreasing terms, and it's also given that sum of these terms is equal to 2n. So you have to prove this inequality. So I'll just show you how to do this. So this you call it S, this one you call it P. This is a product, you call it P. So you have to prove that S is less than or equal to P. So we prove it with Chebyshev inequality. So you take E1 as this expression here, 1 plus A1 plus A1 A2 till this. So this you can say this is S minus 1. And E2 you take it to be this, A1 plus A2, which is equal to 2n. And now you apply Chebyshev inequality here. So you can see that terms are increasing here. Here also the terms are increasing. So you know which inequality to apply. So take term by term product and you take a mean of that. So that will be greater than or equal to the mean of individual terms here. So if the series is both increasing or both decreasing, then you have this inequality. If one of them is increasing, other is decreasing, then the sign changes. Okay, so you know that if you have used this inequality before. So take term by term product. So it will be A1, then A1 A2, then A1 A2 A3, like that, and the final term will be A1 till AN, this one. And you take a mean of that, so n terms, so divide by n. And so this is E1 by n, and this is E2 by n. So E1 you can write S minus 1, E2 you can write 2n, and now you just simplify this. So what's this here? This is S minus 2 here, okay? And this is P, so it's S minus 2 plus P. And this will become, this factor will go away. And 1n will go away with this. So basically you are just left with a factor 2 here. So this is 2 into S minus 1. And now you just bring minus 2 will go out and just bring 1s to this side. You get P greater than or equal to S. So yeah, this is a straightforward application of Chebyshev inequality. If you know this, if you have some practice with this, it's very easy to get. Otherwise it can be time consuming. I mean, I think you can also do it with induction, but it will be quite lengthy. Okay, so now let's look at next problem. Yeah, so this is the lengthiest So there are many equidistant parallel lines, and you draw polygons on it, and you call it frameable if it's possible to draw a regular polygon of n sides, all of which vertices lie on this line, and no line contains more than one vertex. Okay, and you have to show that 3, 4, 6 are frameable, and anything greater than or equal to 7 is not frameable, and you have to find whether 5 is frameable or not. So okay, so this is a lengthy problem. It will need a little bit of research, but it's not that difficult. But it's lengthy. It's lengthy to write it down also. I mean, if you want to write it down properly, all that will be quite time consuming. So, but given that other problems were quite short, so maybe it's justified to have one lengthy problem here. Okay, so take those lines parallel to the x-axis. So the equation will be y equal to -2, -3, -4, -1, then 0, y equal to 1, 2, 3. So above the x-axis, the lines will be y equal to 1, y equal to 2, y equal to 3, and so on. So these are lines which are parallel to the x-axis. Okay, and the difference between two lines is 1. So and now you want to draw a regular polygon, and the vertices of the polygon has to lie on this line, and each line should contain, each vertex, no two vertex should be on the same line, basically. Okay, so first of all, first observation and first realization is that the center of this polygon can be chosen at origin. So this is possible due to the scaling and translation. You just translate the polygon to the center, and then you just scale the lines. So you can bring everything to the, you can scale it and you can translate the lines. So this is the first observation and first realization that you have to see. And after that, you take the first vertex, you locate it, you can use complex number, you locate its coordinates, and then you can get the remaining coordinates by rotating it with angle of 2 pi by n. So pk, you can write e to the power, this take this first one p naught and into e to the power 2k pi by n. Okay, so this will be the coordinate of the kth vertex. So you know all the coordinates, and the thing is that the imaginary part will be its y-axis, so they all have to be distinct integers. So these are integers, and of course they are also distinct. Okay, so when is this possible? Okay, so that's what you have to check, basically. So these are the coordinates. You can write it in this form of your polygon. And if you take the y coordinates, so the first one you put k equal to 0, so it will be just y. So, so the y coordinate will be the imaginary part. So you have to look at all the imaginary parts. They all have to be distinct integers. So the p1 will be, put k equal to 1 here, so you get this. p2, where you just put k equal to 2, and n minus 1, you put k equal to n minus 1. And if you can simplify it a bit, it's similar to this one, just one coordinate will be minus. Okay, so all these are integers and distinct integers. And what I do is I take a sum of these two. That will also be an integer. Yeah, this is an integer, this is an integer. Sum of that will be an integer, so that means 2y cos 2 pi by n is an integer, and y is also an integer, so that means this cos 2 pi by n is rational. Okay, so when is this rational? So this is possible only for certain values. So n can take only 1, 2, 3, 4, 6. Of course, this is from your day-to-day maths. It's kind of obvious, but when you want to prove it, you have to use this thing called Nevis Theorem. So I'm not showing you the proof. I don't know if you have to prove it in the exam, whether they expect it or not. But even without proof, this problem is quite lengthy. So maybe you can just mention it and get away. I don't know. But the proof you will get it on net. You can get it in his book, So only these values are possible. Only for these values this is rational. Okay, so what does that means? That means n equal to 5 and anything greater than equal to 7 are not frameable. So already 2 parts of the problem are proved, and you have to check for n equal to 3, 4 and 6. So for all this it's actually possible, and I'll just show you. So n equal to 3, you just use this. All these have to be integer. So first coordinate will be y, second will be this, third will be this. So if you want to make all these distinct integer, you can choose y equal to 0, and x you can choose to be minus of this. I mean not minus, but an inverse of this. So this will become 1, this will become minus 1. So all this will become 0, this will become 1, this will become minus 1. So all these are distinct integers. Then you can easily write down the coordinates. So p0 will be x plus iy, p1 will be this into just rotated by 2 pi by 3, p2 this you again rotated by 2 pi by 3. So these will be the coordinates. Same thing you can do for n equal to 4. Just write down so here you'll have 4 now. So you have y, and this will be x, this will be minus y, this will be minus x. So all these have to be distinct. So what I can do is I can take y equal to 1 and x equal to 2. So this will be 1, this will be 2, this will be minus 1, this will be minus 2. So all these are distinct integers, so they will lie on distinct lines. So, and you can write down the vertices easily. The first one is just x plus iy, so it's 2 plus I, and p1 when you want to find out, you rotate it by e to the power I pi by 2. Okay, so basically 2 pi by 4 is will be pi by 2, so this is equal to I. So basically you just multiply it with I, so this will become minus 1 plus 2i. Similarly, when you want to find coordinate of, so this should be p2, so multiply again with an I. So this multiplied with this will be minus 2 minus I. This will be p3, sorry. So this will be again this one multiplied with I, so it will be 1 minus 2i. So similarly for n equal to 6 you can do it, but please do it yourself. I mean it's not difficult, just you will have 6 of these vertices and you just choose the values accordingly, and maybe you can mention it in the comments, the answer you get. Okay, so this is the last problem. So there is a 5 by 5 board, and there are rectangles which they call it stromino of 3 into 1 size, and you have to cover this board, and you have 16 of them, and every square is covered by 1 or 2 strominos. Okay, and you put it either horizontally or vertically, and each stromino covers exactly 3 squares. Okay, so you have to tile it with a 3:1 rectangle properly. So this is a trick question, and I can recall something like this was asked to me once in a job interview at a big company. So the way to do it is that you have to observe these gray squares. So every stromino, no matter where you place it, it will cover some of these. If you put it here, it will cover 2. If you put it outside, it will take 1. So from here you have to make your arguments. So each stromino covers at least 1 gray square. That's, you start with this. So you have 16 strominos, so they will cover more than greater than or equal to 16 gray squares. But you have only 8 of them, so that means each gray square has at least 2 strominos on them. Okay, but you are not allowed to have more than 2 strominos, so that means each gray square has exact 2 strominos, and it also implies this: each stromino covers exactly 1 gray square. Okay, yeah, so this is clear. Each gray square has 2 strominos, so 16, and then it's already covered, so each stromino has will cover only 1 gray square. But you have to look at the stromino which is covering this middle square. So that will have two, that will cover two gray squares, the center one, and that is a contradiction here. So it actually cannot be covered. Okay, so this is your proof. And yeah, so it was interesting to see this type of problem. Yes. Yeah, so I hope you enjoyed the solution, and if you have anything to say, you can just email me, you can write in comments. Otherwise, I hope you enjoyed the video, and thanks for watching. Okay, I'll see you next time. Bye.